In this video, I will talk about the uncertainty of the sample mean. When we are making inferences about a population, we often draw a sample and compute the mean of a variable of interest. We use the mean in that sample to say something about the mean in the population. Let's make a more concrete example. Imagine you would like to know the mean weekly sales of a population of 2,000 stores. You're doing some market research, and that's what you would like to know. So imagine that you have data, and here I'm printing only 250 stores. So each number here represents the sales in pairs of shoes per week on 250 stores. Okay, in reality, you will get a small sample of stores, but for now, let's assume that we get to see all 2,000 stores. Okay, so what do we see here? We see some stores that sell a lot of shoes. This store that I have highlighted here sells 49 pairs of shoes a week. This store sells 11, so much less. Other stores sell 14 or 52. So you can see there's a wide variation in the level of sales of shoes across stores. Maybe it's better to see this data as a histogram. So this is the distribution of sales across all 2,000 stores. Okay, you can see that there is not necessarily one mode, but two modes probably. Some stores sell lots of shoes, almost 60 or around 60, and some stores sell very few pairs of shoes. Now, if we would like to summarize this population, and at the moment we're assuming we can see the population, that's not what you can see in reality, but we're assuming that, we could use, for example, the population mean. In this case, is 28.66. We're going to use this number, so remember it. We can also think about the dispersion of these numbers, so how much they spread out around the mean. And in this case, we can summarize it with the variance, or as I have written here, the standard deviation. Okay, it's 9.02. So these two numbers tell you something about what is the sort of the average number of sales and also the dispersion around that mean. So let's look again at these numbers. I have arranged these numbers in a very particular way. It's kind of a rectangle of numbers with 10 rows. So we can imagine that each column in this table, it's a sample of 10 stores. So let's say we take this first column and compute the mean. We get a mean of 24.6. It's very different from the 28 that we saw the population mean. What about the next columns? We can continue with the second column, 35.6, much higher now. The next, 27.9, the next, 28.6, and so on and so forth. Now, what you can see here is that even though the means are different, they all kind of are closer to the population mean than the observations. Remember, with the observations, we got to see weekly sales of 50 or weekly sales of 11, but now all the means are somehow between 25 and 35. And many of them fall around 27, 31, 29, very close to the population mean. So that's a very important result. The means have less variance than the population. Let me say it again. The dispersion in the data that you see is much larger than the dispersion in the means we're computing. Why is that? Well, the answer you can see in this table. What happens is that sometimes you have stores that sell a lot, and sometimes stores that sell very little. If I happen to pick up 10 stores randomly, I will mix sometimes high-selling stores with low-selling stores. And they compensate, they kind of balance each other. The second sample, it's relatively high, has a relatively high mean, 35.6. That's because we just happened randomly to pick up stores with very high sales and very few stores or almost no stores with very low sales. And the opposite is true for the first sample. But in general, for when you get a sample, for every store with high sales, you are likely to pick up a store with low sales. So remember, the means fall all closer together because every sample has a high and low selling stores, on average. So let's look at the population again. And let's say that we take samples of 10 and compute the mean, another sample of 10 and compute the mean, and we do that for 25 samples. So we have here two histograms. On top, the histogram of the population. In the bottom, the histogram of the means of 25 samples of n equal 10, so samples of 10. All these sample means kind of pile up close to 28.6, which is the mean of the population. Let's say, because we're doing this with a simulation, we could pick up many more samples. So instead of 25 samples, let's take 250 samples. What do you see? Well, we still see that they are all bunched up together around 28, but the shape already looks very symmetric. It doesn't look anything like the shape of the distribution of the population. So let's just go crazy and get like 5,000 samples. We still see the center of this distribution of means very much, in the center of the distribution in the population. So the population mean, but we do see that the shape looks almost like a normal distribution. Let's say we repeat that, but now with samples of 50. So before all of this we have been doing, we were taking samples of 10, computing the mean, and creating a histogram. So if I take samples of 50, what we see is pretty much the same, with one important difference, namely that the means of samples of 50 tend to pile up way closer, much closer to the population mean. Why would that be? Well, remember that we used to get very low means or high means when randomly or accidentally we would just have a sample with lots of high selling stores or lots of low selling stores. If you get a sample of 50, most likely you will have high selling stores and low selling stores in every sample. So they will all kind of balance each other out. Okay? So this is an important result. And we can summarize it in the following way. The means, when you take samples from a population, the means pile up around mu. Mu is the Greek letter that we're going to use to talk about the population mean. In this case, it's 28.66. Second, the sample means vary less than the population. You can see the dispersion, you can see the variance is much smaller. Okay? Because of what we said. High numbers balance each other out with low numbers. 3. It starts looking like the normal distribution. So once we get lots of samples, we can see the shape of this distribution. Okay, it's almost like the normal. And if we take larger samples, the distribution of those means, it's going to be more concentrated around the population mean. Here we come to an important result about the distribution of the mean of a sample. Given a sample of size n, so n is a number, in our case it was either 10 or 50, of independent and identically distributed random variables from a population with mean mu and variance sigma square, the sample mean, we here write the sample as x bar, has mean equal to the population mean and a variance equal to the population variance divided by n. So the larger the sample, the smaller is going to be the variance of the distribution of the sample mean. In addition, we have a rather remarkable result called the central limit theorem that says that as n increases, as the sample size increases, the distributions of x bar of the sample means become closer to the normal distribution. That is to say, for large n, the mean is distributed approximately normal, centered on mu, centered on the population mean, and with a variance equal to sigma square over n. Okay, these two results are remarkable in one word. So let's see how that be sort of applied to our inference problem. We have again the histogram of the sales in the population, that is to say, these are all the stores we have. The central limit theorem says that samples of size n will be centered at mu, that is to say, 28.66, and have a standard deviation of sigma over square root of n. Okay, I took the square root of sigma squared over n. What is that number? For a sample of 10, we can do the calculation and obtain 2.85. If the sample increases, this number will become smaller. Remember that for higher samples, we have a smaller variance of the means, and sigma over square root of 50 is 1.28. So let's look at these pictures now. These are the histograms that we collected before. The histogram in the top is for sample of n equal 10. This is the distribution of means that I simulated of samples of size 10. If I compute the mean of those means, okay, the mean of those means, I obtain something close to the population mean, 28.64. The standard deviation of those samples that I computed, those sample means, is 2.83. Now look at that number for a moment and compare it to the number we said earlier, sigma over square root of 10, 2.85. It's very close. It's not identical, of course. This is a random process that I generated with my computer, so of course it's not going to be identical. But it's converging to the theoretical number or the theoretical prediction of the central limit theorem. For a sample of 50, we obtain a distribution of means, again, centered on the population mean. The actual mean of sample of means is 28.63, also very close, and the standard deviation of this means is 1.26, which is a bit smaller than 1.28, but very close. Okay, so the central limit theorem has this prediction that you can actually corroborate from the simulations. Let's focus a little bit on this. If we have this theoretical result, the central limit theorem, we can start making claims or statements about the mean. So let's look at this picture and draw it a bit nicer. So what is that? That's the same picture, I just used a different scale. It's a normal distribution, centered around 28.66. I rounded up the number to 28.7, and with a variance of 1.28 squared. It turns out that if you create an interval, 2 standard deviations on each side of the mean, that interval is going to create a region such that the area under the curve, it's 95%. What is that? Well, we centered at 28.7, and it's 2 standard deviations on each side of 28.7. So 2 times 1.28 on each side. So we know that if we take sample means, 95% of the time, or with 95% probabilities, they're going to be falling between 26.1 and 31.2. That's a prediction from the central limit theorem. So let's look at this more visually. We have computed an interval that encloses 95% of the probability under the distribution of the sample mean. That implies that if I keep taking samples and compute the mean, those means are going to fall inside the interval. Not always, but 95% of the time. Sometimes they fall outside, but most of the time they're going to fall inside. That's the idea. If I compute new samples, they're all going to fall with 95% probability inside this interval. So let's state it properly. The probability that a mean of a new sample of size n is larger than mu, the population mean, minus, and now I'm using the exact number, 1.96 times sigma over the square root of n, and smaller than mu plus 1.96 times sigma over the square root of n, it's 0.95. That's the same statement we made before, just a little bit more rigorous. And if you want it written purely mathematically, you can write it like this. The sample mean here is a random variable, so we can make statements about it, probabilistic statements. And yeah, the new sample mean will fall within this specified interval 95% of the time. So this probability is 95% or 0.95. Okay? If you ever studied confidence intervals, this looks similar, but we're not quite there. This is not a confidence interval yet. This is just a statement about the distribution of the mean. Now, what is the issue? In real settings, we cannot take sample after sample. We only have one sample. We take one sample and we have to make inferences about mu. Okay? In real settings, we don't know mu, and we don't know sigma. We can only take a sample and compute the sample mean, x bar. Now the question is, can we use the sample mean and the sample deviation to make inferences about mu? That is the question. Okay? So we're not quite there yet. We're almost there. But this is the main result from a statistics that we're going to use to start building confidence intervals. But for that, we need to wait until the next video. Goodbye.